There are two variations in solving these type of problems. The first one is from a perspective view, and another one is from a bird's eye view, and the way how you solve the problems are pretty much different. Let's go through the perspective view, all right? So let's say that we have a box, and someone is trying to push it with a force at a weird angle like this, okay? 5 newtons down 30 degrees towards the right. We know that naturally the box will glide towards the right like so. Okay, but the picture we have on the left is not a free body diagram. It's known as a system diagram. In other words, a picture just showing you what's going on. For one thing, how should the arrow always be pointing? Good, away from the box. And that's how it should be shown in the free body diagram. So you got a 2 kilogram mass, and you have a force acting in an angle that looks like that. Okay. We also have the force of gravity pulling it downwards, and the normal force matching everything dollar for dollar. It's one of the purposes of the normal force, to guarantee that the object won't sink to the ground. Okay, and the number will increase or decrease as necessary to balance the budget. If you notice the way how I've sketched it out here, no, you don't have to draw it to scale, but I actually tried drawing it to scale here. Because you'll notice that the FG plus the vertical component of FH is added together to the same length of FN. Because our F net Y is going to be equal to, you guessed it, 0. And do we draw our F net force in here? That's right, we don't. Okay, this is all that needs to be drawn in the picture. However, I know that it's hard to see angles and figure out what's going on. So if you want to, you're more than welcome to just draw out a dotted diagram, reminding yourself when to use sine and when to use cosine, and I'm fine with that. I'll pretend as if none of this existed. All right, but in an official free body diagram, you're not supposed to include that information. Hey, we'll just leave it as is for now. Now let's start solving out everything, okay? Since this is technically a two-dimensional problem, let's solve the vertical dimension followed by the horizontal dimension. So our F net Y is equal to our normal force, subtract the force of gravity, subtract the vertical component of the hand. Since it's not going to fly from the sky or land to the ground, it's going to net to a value of 0. And the only number that we can really solve for here now is Fn. Because Fg can be solved, Fg is equal to mg, and our Fh was given to us as well, including its corresponding angle. So it is solvable. Do we need this for this problem over here? No, not really, but I'm just showing you on how you'd set it up. It's very important for tomorrow's lesson. Okay, so that's why I'm going through it. So even though in this case over here it's obvious it's not going to sink into the table, we're solving for the normal force to solve for friction, tomorrow's episode. But the x dimension we should be able to readily solve. Our F net x is just equal to FH in the x dimension. And since it's opposite of 30 degrees, it's simply equal to FH times the sine of 30 degrees. Sine of 30 always gives you half the answer, so half of 5 is 2.5 newtons to the right. So that's our F net. Do we need to use the Pythagorean theorem? Well, we already studied that F net Y is equal to 0, so it's completely unnecessary to write that down. No, don't even bother. Just know that your F net is equal to 2.5. Lastly, F net is equal to MA, so therefore A is equal to F net with M brought down below divided by M. 2.5 divided by 2 kilograms gives us 1.2 meters per second squared towards the right. All right, so this is a two-dimensional problem, but we know that in the vertical dimension it goes to 0. And in that case over there, don't even bother using the Pythagorean theorem. Keep that in mind. That's a common mistake I see. On the other hand, with a bird's eye view, the outcome will be different, and that will be our next example. All right, let's say that we have these two friends over here. They're fighting over who's going to pull the ride. If they were to refuse each other, they would be at a standstill. But let's say that they both decided to cave in and pull the wagon. All right, where Calvin pulls with a force of 5 newtons north 50 degrees east, and Hobbes decides to pull with a force of 6 newtons east 25 degrees south. All right, so this is a two-dimensional problem. How are we going to solve it? Yes, there's two different ways, component method and trig method. Which one am I going to use? Did I hear component? Sure, we'll do component method first. All right, remember that this is a free body diagram, or this is a force-based problem, so you need to draw a free body diagram first. All right, so we have this 4.5 kilogram wagon, that's pretty light now, and two forces acting on it. Okay, one force 5 newtons north 50 degrees east, and another force east 25 degrees south. And And that's it for the free body diagram. If you're wondering about gravity, remember this is reading a treasure map. Gravity technically would be going into the page. Okay, and then the normal force will be sticking out of the page. That's in the third dimension, so we don't need to worry about drawing it. Okay, we just know that the gravitational force and the normal force in the third dimension will net to 0, so don't worry about that. Okay. Now, if it helps for you, as I mentioned before, maybe you want to draw these faint little lines for your referencing. All right. For example, this 50 degrees is north 50 degrees towards the east, and the other one is east 25 degrees downwards. And yes, this changes out the outcome of everything. After all, for the red component over here, it's opposite of 50 degrees, so you'll want to use sine for this component. And for the blue, you'll want to use cosine. And with this other triangle down here, things have flipped around because of our referencing. This time around, we're not measuring relative to north or south, we're measuring it relative to east. And that's why the opposite side will be solved by using sine for the blue component and cosine for the red component. Now let's start solving things out. F net x is equal to fcx plus fh in the x dimension. Remember the shortcut from the last unit? All you have to do is multiply the hypotenuse by either sine or cosine. That's it. So as for Kelvin, the horizontal component is opposite of the 50 degrees. So to solve for fcx, we're going to multiply our 5 newtons by the sine of 50 degrees. Like so. I know it's all pre-animated out. As for Hobbes, the horizontal component is adjacent to 25 degrees. And as it's adjacent, that's why we're going to multiply by the cosine of 25 degrees. Crunch it out with your calculator, and you'll get to the answer here. Since Kelvin is pulling towards the north and Hobbes is pulling towards the south, we know that F net y is equal to force of Kelvin, y, subtract the force of Hobbes in the y dimension, as they are opposing each other. Remember, that's why we want a coordinate system. That reminds us when we're going to use a positive and when we're going to use a negative. As for Kelvin himself, we'll do this raw right here. Fc is equal to 5.0 newtons. And this vertical component is beside 50 degrees. That's where we're going to multiply by the cosine of 50 degrees. And as for Hobbes, he's moving the opposite way. That's why it's a minus sign. South is negative from our frame of reference. Force of Hobbes applied is 6 newtons. And that blue vector is opposite of 25 degrees. That's why we're going to multiply by the sine of 25 degrees. Booyah, like so. And booyah, an answer. At this moment, I always recommend that you pause and just briefly double check your work. Whenever you're solving these problems, you'll notice that in one dimension you'll be using sine, and in the other dimension you'll be using cosine. Or if you're using cosine in one dimension, you'll be using sine in the opposite. I'm not asking you to automatically switch over your brain so that when you see cosine for the first one, you automatically use sine afterwards. I've always recommended that after you're done with one component, just block it out of your memory. Don't even stare at it. Solve for the other dimension. And if for any reason in your next dimension over here, let's say that right at this point over here, you wrote down cosine of 25 degrees and you compare it on top, you'll notice that one of these two is wrong. And that gives you a chance to pause and reflect upon where the mistake is. That's a good tech tip there. All right, the next good tech tip is how would you solve the next part? You probably want to draw another triangle. You'll see that this triangle has a very long horizontal component and a very short vertical component. That way, when you solve for the angle, if you draw the triangle like this, expect it to be a very small angle, definitely less than 45 degrees. Okay, remember to use the correct notation. Don't use c squared is equal to a squared plus b squared. Instead, state that f net is equal to the root of f net x squared plus f net y squared. Sub the values in, you'll get to an answer. And as for your angle, in this case over here, it's going to be equal to f net y divided by f net x for your inverse tan. After you've shown all your work, you're going to get an answer over here, but that's not the final answer as we're solving for acceleration. And hopefully you know by now, to solve for acceleration, you divide F net by mass. Go through that, and that's it. You're done. Oh, but you said, sir, wait, you haven't solved for trig yet. I'll give you a heads up on how you'd solve it. With the trig method, don't forget that you're solving for a resultant vector. So with these two smaller vectors over here, you need to connect them from head to tail. So let's go and magically do it right from over there. Yes. Vector 1, vector 2, right? Vector 1 plus vector 2. And here's where we're going to draw our FNet, because our FNet technically is our resultant vector. Remember, this is not a free body diagram. That's why the green vector can show up. But in a regular free body diagram, you should never draw the FNet, okay? Because that's what you're trying to solve for. But here we're trying to draw a triangle. So in the triangle, our resultant vector is our FNet. Okay, with this problem over here, this angle here we don't know yet. This angle we can't solve. But this angle up here, there is a workaround towards solving it. We see that FC is north 50 degrees towards the east. In other words, if you use the Z pattern, over here it's also 50 degrees. As for Hobbs, it's east 25 degrees towards the south, so we look for the complementary angle of 25 degrees. After all, it's a vector that points like this. So if it's 25 degrees up here, down here it should be 65 degrees. If we call this side C, then angle C is equal to angle A plus angle B, and 50 plus 65 gives us, excellent, 115 degrees. We already have FH. We already have FC. So what we effectively have here is a side angle side. Side angle side can always be solved using cosine law. Sub everything in, crunch it out. Just know that this will not tell you your final answer. It will only tell you the magnitude of your final answer. All right, so as for the direction over here, you'd first solve for angle B, which is not the correct answer yet, because don't forget that FC is also east 40 degrees towards the north. So to find out your FNet, you'll have to take your theta, or your angle B. So the angle of FNet is equal to, I guess in this case over here, it's 40 degrees. Subtract whatever your angle B is that you can solve by using sine law. Okay, and you'll get to the same answer. Yeah, I'll leave it at that. Good luck with your homework tonight. Just kidding. Let's do our homework. All right, so two people are pushing a car of mass of 2 metric tons. They each push with a force of 320 newtons, and here's our free body diagram. Booyah. Calculate the acceleration of the car assuming no resistance. Don't forget that the normal force is sticking out of the page, and the force of gravity is going into the page. All right, so that's in the third dimension. Don't need to worry about that. Okay, but here in this case over here, in this problem, we probably want to just break everything down so that we can clearly see how the angles affect your final answer. Okay. So your FNet in the y dimension, when you go through the math of this, that's equal to F1 times the sine of 15 degrees, subtract, as F2 is pointing downwards, 15 times opposite, so sine of 15 degrees. Yeah, FNet y equals 0. So all we're left with is our FNet x. So our FNet x is equal to F1 times the cosine of 15 plus F2 times the cosine of 15 as well. Since FNet y is equal to 0, we don't need to use the Pythagorean theorem to solve for FNet. FNet is just equal to 618. And we're done. Oh, almost done. Got to calculate the acceleration. What's the acceleration? That's right, FNet divided by m. So take your 618, divide by 2,000, and you have an acceleration less than 1 meter per second squared. Goodies. Now, what if there was a resistive force? Well, the resistive force would be pointing backwards. Good, I have it pictured out over here. All right. So our FNet y is equal to 0, but our FNet x is equal to F1 plus F2 subtract the force of friction of 425. That gets us our FNet. We then take our FNet and divide by the mass, and we'll realize that our acceleration is peanuts this time around, 97 millimeters per second squared. If you write it down as 9.7 times 10 to the negative 2 meters per second squared, that's fine with me as well. A canoe of mass of 70 kilograms with a paddler of mass of 55 are in a river. Now remember that these two are two objects that are together. They're glued together. So they should be within the box. So you could just write down 125 kilograms. But just to let you know, 70 plus 55 will give you 125. There's two forces acting on it. First off, the river current is pushing the canoe towards the east, and the paddler is trying for his or her dear life to try to paddle it towards the northwest. That's it. Don't add anything else. Remember that gravity is going into the page and the normal force is coming out of the page. That's in the third dimension. This is a bird's eye view problem. A good way of figuring that out is by looking at the coordinate system. All right, northeast. If it was like forwards and backwards and up and down, then you know it's a perspective view. And in a perspective view, f net y is equal to 0. But this is a bird's eye view, so anything is fair game. So let's sit down and calculate it out. I'd still recommend just using the component method. I'll leave the trigonometric method as a personal exercise for you, where you're just really connecting them from head to tail. So you have vector 1 plus vector number 2. Solve for this mystery meat. That's all it is. But by component method, we first want to solve for the x dimension. So the force of the rower, don't need to break it down into components. It's just 15 newtons. As for, the river. As for the paddler, you'll notice that FP is in the opposite direction. That's why it's minus sign, and 38 is far away from that component. That's why we're doing the sine of 38 degrees. As for the y dimension, the river does not have any vertical component, but the paddler does. And this is beside the 38 degrees. So that's why we're going to use FP times the cosine of 38. Once again, with these two parts together, you probably want to draw a brief little sketch, a blip towards the right, and a huge value all the way towards the north. That way you know for sure that your theta over here is going to be greater than 45 degrees. It's a good check. All right, you'll glue them together by using the Pythagorean theorem. Find out the angle by using inverse tan. And as mentioned, the angle is going to be huge. Finish it off by finding out the acceleration, where you divide the F net by mass. And there's your answer for number 4. Curious about number 5? Start off with a free body diagram. We have two tugboats, and they're both tilting away from each other, kind of like the Kelvin and Hobbes problem. You'll see that our free body diagram has north, east, southwest, so this is a bird's eye view. With that, break everything down into its components, and then isolate and solve for the mass. Let's go and do that. All right, so we know that our F net x is equal to F1 times the cosine of 16 degrees plus F2 times the cosine of 9.0 degrees, as both of these are beside the angle. As for our y component, again, this is very similar to Kelvin and Hobbes. F1 will be in the positive direction, F2 will be in the negative direction. As these two green vectors are opposite of the angles, that's why we're going to apply sine to both of them. You'll see that the red component is really long, 5 sig fig. Our vertical component is only 4 sig fig. So guess what? The angle that you'll have will be definitely less than 45 degrees. Sounds good to me. All right. Not that you have to solve for the angle, because the angle is already given to you. Instead, you're more concerned about the mass. Since F net is equal to mass times acceleration, then mass is therefore equal to F net divided by A. So we have our F nets that, we still got to solve. There you go. 46,862 divided by the acceleration of that very slow speed. 1.4 times 10 to the negative 3 meters per second squared, as is given to you. And then that'll tell you the corresponding mass of the tanker itself. Number 6, the fun one. So you have a balloon. The balloon is being pulled up by its buoyant force of, 3,800 newtons. That's the buoyant force, the force of the balloon pulling upwards. The balloon also has a weight of 3,000 newtons. If you want to convert into a mass, you can, Not that you need it for here, but if you're curious, if you want to find the mass is the force of gravity divided by acceleration, right? Fg is equal to ma, so m is equal to Fg divided by a, or g for this case over here, Fg divided by g. Not that we need a number here, so it's not important. But what is important is that there's two other forces acting on this. First off, person B pulling towards the left, and the question is, what about person A? Or person C, sorry. Person C. How should they be pulling so that this balloon doesn't fly off into the sky, nor does it sink down to the ground? For that, we need to find out our y component of Fc. If we don't want it to fly off in the sky, we know that our F net y has to equal 0. So 3,800 newtons upwards, subtract Fb times the sine of 40, also subtract Fc times the sine of whatever the theta is, has to equal 0. There you go. 3,800, subtract, oh yeah, I forgot the 3,000. Woo! Glad that this is on a PowerPoint. All right, so 3,800, subtract the 3,000 newtons downwards, subtract 540 newtons times the sine of 40 degrees, subtract FCY will equal to 0, but here we have our FCY. So our FCY will be the solution. You need to pull down an additional 452.89 newtons in order for your F net Y to balance out. Okay, but what happens in the horizontal dimension? Well, since you have your value for your FC in the Y dimension, you could solve for your FC in the X dimension. All right, whatever method you want. You could use a trig method, or you could also use the Pythagorean theorem solving for it. And when you calculate out what that value is, you find out that this works out to 534 newtons. Well, 534 newtons towards the right versus 413 towards the left. You could find out the corresponding acceleration. That's true if you solve for the mass. But really, it just asks you what happens to the horizontal component. Since it's being pulled harder towards the right, the system will accelerate towards the right. And that's it. You're all done. See you in another episode.